to design rather than writing Verilog code. So they have a in-house graphical programming tool that uses ASM chart to design, to start the initial design of digital system, right? So the tools in designing a digital system, actually there are three parts in it. State diagram is one part. They are mainly used for designing controllers, because controllers are specifically state machine. They are typically more machine where the states are the output. So that's why state diagram is very useful in designing controller. So most of the controller are designed using state diagram. However, for more complicated system that require a controller, it's not so you have a controller and then you have some other operations that the controller control. The whole system design normally is use ASM chart to design. Now, if you do not know, if for people who don't use ASM chart, they have to use two separate tools. They have to use both the state diagram and register transfer notation to specify the register transfer operations. So we will go through this quickly. I will not go through this in detail because a lot of the lecture slides are in words that were designed for you to read on your own. I will just cover the basic enough for you to start, and then I'll leave the rest for you to read on your own, so that we can cut the time for more demonstrations how the ASM chart is being drawn. Okay. So before I go into talking about the tools, I want to talk about what is register, what is RTL. In the industry, people always talk about RTL. So what exactly is RTL? Now, RTL means register transfer level, which means we are describing the hardware at the register transfer level. So, but what is register transfer level? It means we look at the registers and what happened in the register. What are the registers are doing? So the focus of RTL level is describing what is happening in the registers and what the registers are doing. And by doing so, we can describe the hardware and design at this level. They are not as detailed as gate level design. You have to describe all the gate, what input, what output, and they describe the flip-flop, what are the flip-flop input, and then how at what time the flip-flop will be latch or not latch, or trigger or not trigger, things like that. This one will be at a higher abstraction level. We don't specifically look at all the gates. We just talk about what data are moved into the register and how the register are dealing with the data. Either they do addition, they do shifting, so the focus will be what type of register operation is happening. Typically will be algorithmic, either I'm sorry, not arithmetic, addition, multiplication, division, or logical, which is AND or NOT, or shifting, which is the type of operation that can be carried out using the registers. Of course, that includes load store as well. You have to load from the memory into the register and store the data from the register to the memory. So these are also part of the register transfer operations. Now, why we want to describe hardware in the RTL level? The reason being is a functional digital system are sequential logic, and sequential logic we use flip-flops, and when we group flip-flops together, they become registers. So that is the main reason, and that is why it is one of the most popular level of description of hardware in the design industry, in the hardware design industry. And it is at the highest abstraction level of describing a hardware that can still be synthesizable, provided that you follow some guidelines, right? Some guidelines need to be followed for that. Another reason is it is modular. It is actually when we do register transfer level description, we can split a very complex system into smaller modules, and then that jive nicely with the hardware design industry. All right. So this is describing what type of operation that register can do, and I leave it for you to read. If you have some hardware background, you know that we can do shift in the register, we can do counter with the register, load and store operations, data movement, how to move data from one register to the others, and so on. So I'm not going into detail. You can read this. All right, let's talk about let's talk about the fundamental of digital system. Typically, when we describe a digital system using RTL level descriptions, we talk about the set of register, what are the operations that can be performed on the data stored in the registers, and then what are the sequences of operations, how the operation being scheduled, or so what operation happened after this operation. So when you look at these three parts that is specified in the RTL, hardware description of a hardware, we can split it into two parts. And this is common in all digital systems. So the digital system are typically split into the data path and the control logic. In this, in the RTL, the set of register and the operation that are performed in the register is sitting on the data path. The control that supervises what is the time these operations are happening in the hardware system is specified in the control logic. So it actually partitioned nicely in the hardware in the RTL. So this is another reason why RTL is a common level of description for hardware, because it jive synchronously and congruently in describing a hardware. We can perfectly partition a digital system into the data path and the control logic. At the same time, it also can describe the registers, the operation in the registers, and then when these operations happen. So the way to look at it from a completely beginner's point of view is by asking questions. So when we look at the data path, to know that this is the data path, you ask the questions. What is happening in this state, in the present state? So the data path perfectly describes what is happening in the present state. So what operations are being done in the present state. Whereas the control logic is describing what is the time? When is this operation supposed to happen? So the data path is describing the what, the control logic is describing the timing, when this should happen. Is that okay? Am I going too fast? Hello? Am I losing connections?
No. Okay, sir.
Okay. All right. This is a brief look at register transfer notations. I will go through one and then leave the rest for you to read, and then show you how it perfectly match with Verilog. The reason being it matched perfectly is because the language Verilog is actually designed from register transfer notation in the 60s, if I'm not mistaken. When they were designing Verilog, NASA was the one designed Verilog. Verilog was designed by NASA engineers. So what happened is in the old times when the when the digital hardware was not so complicated, people designed digital hardware using pen and paper before they move to the gate. So they were using simple notations, handwritten notation to describe the register operation. Now this is denoting R2 get the data from R1. So in the Verilog RTL descriptions, we know R2 and R1 are both registers, so they will trigger by the clock edge, and then data transfer from R1 to R2 at the positive edge of the clock. So always mean it always happens. So they actually transition perfectly from register transfer notation to RTL in Verilog. This is with conditions. If T1 is 1, then we transfer data. We move the data from R1 to R2, and so on. So there are more notations I listed in the lecture slide, but I will not go through one by one. You can read it on your own. So what type of register operations? Typically, we can group them into 4 categories. One is moving data from one register to the other. Arithmetic operation, we can do addition, subtractions, and so on. Or logical operations, we can do we can check if this condition is true or not by using AND, OR, and NOT operations. There are things that beginners can miss out because beginners always think that logical operation have difficulty in differentiating logical operations and bit manipulations. Typically, for people who are new to hardware design, they do not cannot differentiate the differences of bit-wise operation and logic operations. You need to pay attention in that. Normally, the easy, quick rule of thumb is logical operation produce 1 bit output, because logical operations only interested in true or false. To know true or false, we only need 1 bit to represent 1 as true, 0 as false. In a bitwise operation is we do all the logic operation at every bit. So bit operations actually can produce multiple bits. So that is one of the fundamental difference. If you keep that in mind, it should help you to avoid a lot of the errors in writing hardware. And this is one of the hiccup that new designer always meet. Rule of thumb is always use bitwise for hardware design. Always use bitwise and try to avoid logical operations, right? And one of the most powerful features of RTL and register is shift data. Shift register is one of the most used and most popular common use of register operation, because it's very powerful. One of the most powerful operation of register is the ability of shifting data inside the registers. All right, this is talking about RTL. I will skip this. It covers a lot of the basic of Verilog. I'll leave it for you to read. And here are some of the quick reference. If you want, you can always come back and look at it. All right, I want to stress something about this, and this is something that beginners in Verilog always miss and having difficulty in getting the concept. There are 2 always operation here. For this operation to work, always at A or B, S assign A plus B, S have to be declared as a REG type, but it is not actually a register. REG is a way the Verilog syntax work to to typeset certain variables can only be used inside the procedural block. If you use a procedural block, how do I know that this is a procedural block? Procedural block is all the statement that have the always statement. Anything start with the always statement or a group inside the always statement is a procedural block, and you can only use the reg variable type inside the procedural block. It doesn't mean that this is a register, and it doesn't mean that this is a flip-flop. All right, this is the Verilog syntax. In this case, this will actually translate into a combinational logic. The only way that anything that can be translated into a flip-flop is you have the post-age clock. So only with the post-age clock description that the RA and RD, typically on the left-hand side, this will become registers. Without the post-age clock, this is not a register, right? Even though you have to declare it as an REG type. Is that clear? Hello?
Yeah, yes, clear. What is the S called in if it's not a register?
Yeah, it is the output of a logic gate. In this case, it is the output of an adder. So it is no different from a wire, even though we have to declare it as an REG. Is that clear?
Yeah.
All right. Another thing that is commonly missed out and confusing for beginners to Verilog is the assignment type. Notice that I write the assignment differently in this always block. This is just one equal sign, whereas this assignment is followed by an error, left pointing error. Now, this is denoting two different type of assignment. This type of assignment is called blocking. This type of assignment is called non-blocking. Now, why this is called blocking and this is called non-blocking is because on the non-blocking assignment, the assignment happened immediately after the operations. So what does that mean? In this case, we have an addition operation. So we are adding A to B. So this is operations. After we have finished the addition operations, we will assign the result, the outcome of the operations, into the left-hand side. So this assignment happened immediately after the operations. So this is called non-blocking assignment. Whereas this type of assignment is called blocking. It means I will not assign whatever output of the operations to the left-hand side, even though the operation is finished. So what happened here is I will add RA and RB, but I will not assign the sum to RA. I will keep the sum on this side. And then I will look at the next non-blocking assignment. So I will get the value of RA. Now in this case, RA is not changed because RA haven't updated with the sum of RA plus RB. This RA will still contain the value of this RA. So to highlight this, so the value of this RA is still used by this RA. All right. Is that clear? Because yes, when I'm looking to when this operation is done, it was looking for the value of RA, and then the value of RA here it have not updated because the operation happened here is not assigned to the left-hand side because it's blocked. This is a block. Don't assign first after you look through all the non-blocking assignment. So in this always block, every non-blocking assignment, the value on the right hand side will not assign to the left hand side until all of the non-blocking assignment have been looked at. Is that clear?
Yep.
So there is a mistake in the lecture slide. This is blocking assignment. This is non-blocking assignment. So it's the other way around. Okay.
All right.
So this now why these specific features? The reason being is you think about the operations of registers. Think about the operations of flip-flop. Now the input of the flip-flop will not pass to the output of the flip-flop until there is a positive edge of the clock. Until the flip-flop is triggered. If the flip-flop is not triggered, the value at the input of the flip-flop will not be output, will not be passed to the output of the flip-flop. So this is to mimic the hardware. So this, look at this RA plus RB as the input of the flip-flop. The operation at the input of the flip-flop will still happen, but the value will not pass to the output of the flip-flop until there is a positive edge of the clock. So if you have multiple flip-flop connected at the same clock, so the output of all of these flip-flop will only get the value from the input at the same time, at the same positive edge of the clock. So this is why. Is that clear?
Yep.
All right. Now, because of this, there are some peculiar features in hardware that people will miss. So keep this in mind. You may want to write this down because of the non-blocking features of the Verilog, the netlist, your program. Actually, we shouldn't call it a program. It is the netlist we generate may behave in ways that you do not anticipate, because we are so used to the normal software programming paradigm that we expect the assignment to happen immediately after the operations. So this is not the case. It doesn't happen immediately. You have to wait all of them to be evaluated on the right hand side. Only then it will pass to the right hand side. So think of it in the hardware as a hardware engineers. The input will not flop to the output until there is a positive edge of the clock. So the operation is not controlled by the operation itself, but controlled by the positive edge of the clock. So that's why it is blocking. We have to block the input value from passing to the output until there is a positive edge of the clock. All right.
So just want to explain my thought is that the RB is the input and RA is the output, and we are assigning this output to RA, and only when the clock trigger, the RA will become the output, correct?
Yes. So let me, can I clear? I don't know how to clear this up. Never mind. Okay. As you have said, RA is the output. RA can also act as an input for an operations. So this is input to this addition operation. So RA plus RB is an operations, and then the result of this operation will serve as an input to these registers. So RA is showing the output of these registers, and then RA plus RB is the summation which will fit into the input of the registers, but it will not be flopped to the output until there is a positive edge. So it's like we're holding the value at the input. So RA plus RB are held at the input of the register RA, and it will only flop to the output of the register RA at the positive edge of the clock. Is that clear?
Yep.
Yep.
All right. Yeah, there's something I want to add. I hope it will not add into your confusions. You can look at it as the present state and the next state paradigm. So this is the present state value. to the flip-flop. So present state is RA plus RB. The next state value is RA. So the next state, only at the next state, the next positive edge of the clock, this value will be passed to the output of the flip-flop. So this is the present state and this is the next state. All right, there's another way of looking at it if you are familiar with the present state and next state paradigm. All right, continuous assignment, I will not talk about this. Continuous assignment are typically used in a outdated mode of design. They call the data flow design, data flow level design. Now people typically don't say data flow level or data flow model. People talk about gate level because there are not much difference between data flow and gate level. So even though data flow model is still used, but people typically call it gate level design now. You can look at it because this is not our focus here. So the operators here, I leave it for you to read. It's simple, straightforward. Okay, I want to talk about this, the loop statement. Now, be very careful with using loop statement. When you want to use loop statement in design, make sure you avoid a few things. First, when you see initial statement is a non-synthesizable statement in Verilog. That means anything you write inside an initial block cannot be translated into hardware. So any initial block are non-synthesizable. So it is a bad idea to use initial block coupled with a loop statement to design your hardware. Because any synthesis tools, when they look at initial, they will ignore the whole thing, or they return you with some junk that cannot be translated into hardware. Now, more modern tools may flop you, will give you a warning saying that you're using initial statement in your design. But they know if you do not have any syntax error, it will pass, and this can create a huge problem in hardware design. So avoid using initial statement in your hardware design. But why does Verilog include initial statement if it is cannot be translated into hardware? The main reason is it is used for test bench, for simulation purposes, for managing signals. Signals you want to change only one time, that you can fit into the design you want to test. So initial statement is only used in test bench, right? When you write a test bench, this is the time to use your initial statement. When you write the design, do not use initial statement. So these are some of the loop statement you can use. You can use repeat. You specify how many times you want to repeat. You can use forever. So you don't need to type for open parentheses, semicolon, semicolon, close parentheses. You can just use the word forever. That means it will forever loop. This will be forever loop. All right. You can use a while format similar to C and the for format like C. Now there's one differences in the for format. Inside the for format, in the increment column, in the initialize and then your exit conditions and then your stepping, the stepping statement. In the stepping statement, in Verilog, it doesn't recognize the increment plus operations. You have to use I assign I plus 1. That is the only syntax it accepts. So if you run into problem with your for statement, you use I plus plus, it is not recognized in Verilog. All right? Is that clear?
Yep.
All right.
Yep.
So these are some of the example of using all this looping. I will not go into it. I leave it for you to read, and you can copy this and try it out. All right. In here, yeah, you can declare integer type in Verilog. It recognize. By default, integer is 32 bits. We normally don't use this in hardware design. We use this in the test bench. It normally used in the test bench. It is not used in hardware design. The reason being is it is not describing a hardware. Integer is a software concept. So we typically don't use it in hardware design. So avoid using integer in hardware design, but you can use it in your test bench. If you want a quick and easy variable, you can use it. Here are some examples showing bad way of using integers. Here you're using 32-bit for what? 2-bit operation. This is a 2-bit operation. I is a 2-bit operation here, but you're using 32-bit value. So this is the main reason why we don't use it in hardware design. It is confusing, and it's but this has happened in the hardware before. That's why hardware design industry before, because hardware designer was there was a shortage in hardware designer in the industry, so they recruited software designer, and software designer, they like to make things easy. They do it this way. So this is the way normally software designer will use to design the hardware. Luckily enough, now the synthesis tool are smart enough. They will know that there are wastage here, so they will remove this, and then they will properly interpret this, unroll the for loop, and make it into a proper hardware design. So the saving grace is the design tool now is smart enough to translate this, but this is actually not a proper hardware design engineer will write. For me, I don't design a decoder this manner. This is a decoder designed by a software engineer. All right, so now we have covered all the basics. Let's talk about what we want to talk about today, which is the ASM chart. Now, ASM chart have all the information contained in state diagram, and it also have all the information described in the register transfer notations. So let's talk about what is it. All right. The reason why ASM chart is used is because all the binary information stored in the digital system can be classified as the data to be manipulated by the system, or the control information that we use to control the digital system. So there are two parts, the data path or the control logic. So what are the data path? What the data path do is it handle data. That's why it's called data path. So it manipulates the data in the registers. So that's why register transfer notation will perfectly describe the data path. So in the old days, designers used register transfer notation to describe the data path, and state diagram to describe the control logic. Now, normally the data path is simpler to write down. That's why they don't have graphical tools. They just use a notation, register transfer notation, to describe all the data. They are straightforward. The control logic is a complex part where they have to use a graphical diagram to show how you move, because the timing, to visualize the timing, when this happened and when do you go to this state, when do you go to this state, is complex. That's why they have to use a graphical tool. So the control logic is described using a graphical tool state diagram to describe it. So I leave it to you to read all this. I will not go through it here because I want to talk about the ASM chart. Now, the ASM chart is adopted from flowchart. All right, it is adopted from flowchart. It is a more modern practice. The reason this happened also because there was a big influx of software designer into the hardware design industry. So they bring along some of their expertise and adapted those expertise for hardware design. So they look at this, oh, they say, this can be described using a flowchart with some changes. All right. So it is essentially a flowchart, but with some noticeable differences. So it is a special flowchart for hardware algorithm. It is a special flowchart for hardware algorithm. The differences between a flowchart and an ASM chart is flowchart describe everything in a sequential manner, one after another. ASM chart also describe things in a sequential manner, but with timing constraint. With a timing constraint. So there's a difference. Because typically a digital system is a sequential system because a digital system contains both the control logic, which is the state machine, and the data path, which is the data operations, or both. So we can describe it using a flowchart manner, but what is missing in the flowchart is the timing information. So the relationship between the timing information is missing in the flowchart. The flowchart can perfectly describe the sequential relationship between one operation to the next, but it didn't describe what happened at the positive edge of the clock trigger time. So that is what is missing in the flowchart. So what we need to do is just add that part into the flowchart and it will work. All right, so what do we have in ASM chart? Now in the flowchart, a state box is called a process. A process is describing what is happening, what are the process supposed to be happening. So transition from that, so we will know that a state box is what we describe, what are the operation is going to happen inside it. So the state box will describe what are the operations. The decision box is conditional. It's got the condition. You should ask a question, what happened? Yes or no, true or false. And the conditional box, now this is also another new concept in the ASM chart. And we will talk about it more when we specifically talk about it. And then there is a differentiating concept. In the ASM chart, it also have this thing what we call the ASM block. What is a ASM block? An ASM block is a combination of state box, decision box, and conditional box. We group them together to form an ASM block. So what does that mean? So look at the state box. Now, this is typically how a state box is being described. You have the name of the state, the binary assignment of the state. We can use this, we can use binary number to describe the state, or we can use gray code or one hot assignment. So these are the three very popular. They each have their own advantage and disadvantages. And then what is inside the state box is describing what type of register operation. In this case, we are initializing R to 0, and we output a signal called start. So the start signal is active. We activate the start signal and output it, right? So this is a state box. So we call this a state box. The other is a diamond box where we call decision box. Decision box is where the conditional statement are happening. We can do logical operation here. When we ask a question, if you see the statement, if you are creating a decision box. So every decision box is translated to a if statement. right? Every decision box is translated to an if statement. So in the decision box is also the only item in the ASM chart that split the path. You can see the input path is 1 and is split into 2 exit paths. So decision box is the only item in the ASM chart that split the path of ASM chart. All right. Next is a special box that is only used in the ASM chart. We call conditional box. Now, a conditional box is a follower of decision box. It cannot exist without the decision box. It must follow a decision box. Now, a decision box does not necessarily have a conditional box follow its exit path, but every conditional box must have a decision box on top of it. So it must follow a conditional box. Now what is described inside the the conditional box is the register operation or output. So it is essentially a special type of state box. Essentially a special type of state box, but it doesn't have a state name. It doesn't have a state assignment. It does carry all the register operations and what are the output signals. So far, so good?
Yep.
All right. So what is an ASM block? Now, the purpose of ASM block is to make the ASM chart perfectly describing the phenomenon of clock edge trigger. At the time of the positive clock edge, these are the things will happen. So we group multiple decision box and conditional box under one state box, and we group them together. We call them an ASM block. So in this case, this is one ASM block. Can you see the dotted blue line? Can you see the dotted blue box? Is it clear?
Yep. I can see.
All right, the dotted blue box is one ASM block. And this ASM block have a name. It's called block T1. The name is the same as the state box inside this block. So every ASM block have one and only one state box. So we can count the number of ASM block by counting the number of state box. So as you can see here, I have one state box, two decision box. When we have two decision box, we will expect multiple exit path. In this case, it split the exit path into three parts. So you have three exit paths, and all of these are under the same ASM block. So this T1, this decision box, and then this decision box F, and this conditional box. This is a conditional box. You follow the exit path of a decision box, and you have no state name and no state assignment. So this is a conditional box. And all of this is happening at the same clock triggering edge. And at the next clock triggering edge, it may go to this state or this state or this state, depending on the value of the decision box. Is that true? Is that okay?
Yep.
Yep. Okay.
So far, so good?
Yeah, great.
Yes.
Okay, let's look at an example. So this is one design example. We want to design a counter that counts from 0 to 13. And it is controlled with a start signal S. And when the count reaches 5, we activate signal E and we output the signal. And when the count reaches 12, a finished signal is output and the count stops at 13. Now notice this very peculiar statement. The count reaches 12, I say finish, but why the count stop at 13? Now think about that. Keep that in mind. Why we have to stop the counter at 12 so that we can get a counter count to 13. All right. So let's look at. So I'm trying to walk you through how I will draw this. So let's create a new. I will use a blank one, it's good enough. Now because of the theme, it loads slightly slower. Okay, so I have a blank one. Let's start with a state. We call this initial state first at this moment. Now let's look at. Can you see my screen?
Yes, yes. There's a box there.
Yeah. Okay. Then look back. The counter will only start counting when the control signal S is asserted. So only when S is active that I will start. So I do not know anything yet. I only know that I'm going to start somewhere. So I'm going to start somewhere. So but there is a control signal. So let's use a control signal. So this one is asking S. So if S is not 1, if S is not 1, I will come back here. And let's change this. If S is 0, we'll go back there. If S is 1, I go to the next state. So I need another state. So let's call this S1 at this moment. And this is yes. This is 1. If S is 1, I go to S1. I'm going to do something here in S1. All right. So far, so good?
Yep.
Yeah, great.
Am I going too fast?
Nope, nope.
So can you see how easy for me to draw the state box and the decision box? So this is the power of Lucid Chart. That's why I'm using it. By the way, I have received no commission from Lucid Chart. This is not out of commercial. It's because I like it. That's why I recommend it. All right. Okay. So now after S is asserted, I will initialize and then I will start. Initialize and start. When count reaches 5, I need to output a signal E. And when the count reaches 12, I need to stop counting so that the counter will stop at 13. So to count to 13, I need 4 bits. And so I will need a counter. Counter name is given is A. And there's a signal E. E is only 1 when A reaches 5. If I look at 5 is 101. 5 is 101. So to activate E, I probably have to start checking when A reaches 4. When it is 100, I will activate E. All right. So I may need to do initialization here, or I might do initialization here. Typically, it's a good idea to do initialization at this stage other than at the initial state. It will become clearer later. So there are some operation I may need to do at this stage, and at this some of the operations I may change this when we go into talking about uh, reading from the specification and drawing an ASM chart. Okay, so some of the thing I can do is I can initialize A to 0 before I initialize A to 0 because I want to start to count from 0, and then at the next clock cycle I will start counting. I may want to initialize E to 0. Now this is the only part that, but most of the charting tools have the same problem, so I will not be too fussy about this at this moment. But as you can see, I am initializing the counter, the output E and F here. All right. So I haven't named the state yet. I haven't give it any state assignment yet. I'm just progressing through the specifications. So then after this, I may want to start counting. So A will increment A plus 1. So I'm counting now. It's getting too big. I can resize it, get it smaller, so that I can fit it in. Okay. All right. So right, so my counting start. Now I want to check the value. If I reaches 5, I want to output E. So to check value, whenever you have to do a check value, I know that I have to do a decision box. So I will check E. So I will check E. I will check A. If A is equal to 5, the question A is equal to 5. That's the question. Is A equal to 5? If it is equal to 5, I want to output a value. Yes. Now I use this. All right. Now in the flowchart, this is called terminator. That means you stop from here. But this is not a flowchart. This is ASM chart. This will be the conditional box. So what happened in this condition? I'm checking whether A have reaches 5. If it reaches 5, I want to output E. So E get 1. So I'll output E. E get 1. Again, let's make this smaller. Can you follow me?
Yes, I'm following you.
All right. So I output an E if A is 5. And what happened next? Look at let's go back to the specifications. So when A reaches 5, a signal is asserted and then nothing else. But it haven't reached 13, so we still need to count. So we still need to count. So after that, I will go back and counting. So I still need to count after this. It's bad idea to go out from the side. Let's go out from the bottom, and then like that, and then I can move this over here. All right, so I go back and count again, and then I will continue. I will continue until it reaches 13, until it reaches 12. Then I need to output another signal. So if it reaches 5, then I'm asking the wrong questions. I should be asking, is it bigger or equal to 5? Is it bigger or equal to 5? I output 1 so that I can capture this. And then after that, I have to ask the question, is it bigger or equal to 12? So I may want to change this to another decision box. So to check, is A reaches 12? If it is no, all right, let's show all the no. The no will go back and start counting again. So this is no. So if it is yes, we finish. Yes, we finish. And then after this, this is not a complete ASM chart unless it can go back to the initial state. So after finish, you should be able to go back to the initial state. Right, this is too big. All right, so we have quickly draft the ASM chart for this counter. It's count to 12, count to 13, I'm sorry. Count to 13. If it reaches 12, I will stop count. Now, here is the question. Why I stop at 12 when I want to count to 13? Does anybody knows? Hello? Anyone? Want to take a guess? Why I stop at 12 if I want to count to 13?
Is it because of the most significant bit it starts from 0 to 12, so it's altogether 13?
No. 12 in 4-bit binary value is 1100. 13 is 1101. So there are 4 bits. We use 4 bit to represent 12 and 13. You want to take another guess? Reminder, remember I say something about ASM chart have this extra information called the timing information. Can you take a guess from that hint? Hello? You want to know the answer?
Yes.
Yeah.
Or
I want to know that.
I can give you another hint. SM block. Let's look at how many SM block we have here. Okay. How many SM block we have here? We have the initial block, 1. We have this block, 2. This block, 3. This is not a block. And this block, 4. We have 4 blocks here. So remember what I say about SM block? What is the peculiar thing about SM block? Do you remember? So what happened here? Okay, let's look at this from the clock perspective, the clock signal. Imagine we have a clock signal coming in. We have a square wave coming in. This happened at clock 1, yes? So when clock 1 come in, I will check S. If S is 1, when clock 2 come in, this will happen, yes? This happened at clock 2, correct?
Yes.
All right. At clock 3 come in, it will go to this here. It will start counting up, yes? It will only start counting up at clock 3. Correct?
True.
Yep.
So here, what is the SM block here for this block? Look at the SM block of this box. This. So let's include another shape. I include a rectangular. I want to encapsulate and I want to include all this. Here. Opaque. Go to the view here. No view, so that I can show. All right. So let's change the line. All right. So I have shown all these things. You see, I'm checking A is smaller than 5. I'm checking output E as 1. I'm checking A if it is reach 12. All happen at the same time. I'm counting up. Remember the blocking assignment?
Yeah.
So what happened here is I am counting up, but the count value is not shown in the output. So clock 1, I'm checking S. Clock 2, I initialize. Clock 3, I am counting up. But what is the value of A here, output? Is it 1 or 0?
0.
0, yes. A is 0, but the count is already count up, remember?
Yeah.
The count is already count up. So at clock 3, this one count up. But this one is still 0, not yet counted. So keep that in mind. So when I check A, I'm checking this A or checking this A?
Left side.
The one at the left side, correct. I'm checking the one at the left side. So the E will only set when the one on the left side according to the value on the one on the left side. Because E is checking A, right? If A is smaller than or equal to 5, if bigger or equal, it should be bigger or equal to 5. Okay, that question is wrong, doesn't matter. Bigger or equal to 5, then E is set to 1. I should probably change this. Oh, this one I have to send to the back. Where's the grouping? I'm still confused with the Microsoft Draw. Microsoft Draw, I can just right click and say group, send to the back. never mind then. Okay. So this one, I only check this. When I check this, I'm checking the one on the left-hand side, so it's still 0. So when I'm changing this, I'm still checking this value. Same here. When I'm checking A, I'm checking on this value. So imagine when I reach 4, when I count, my count reaches 4. So let's say the count reaches 4. When I say count reaches 4, I mean the output here is 4. All right, the count here is 4. So when here is 4, that means here is 4 plus 1, yes? When the left-hand side is 4, the right-hand side is 4 plus 1, correct?
Yes.
So 4 plus 1 is 5, correct?
Yep.
So here is 5, but A is still storing 4. So when I check A, if it is bigger or equal to 5, if it reaches 5, I will get a false signal, correct?
Yeah.
You will get a false signal. So E will still be 0, correct? I will not set E. It is false. So go back, I will increment again, correct? Hello?
Yep. Yeah.
All right. So here is the questions. When I loop back, what is happening here when I'm looping back?
The counter increases or what?
The question is when? When does the counter count up? Is it at this clock cycle or the next clock cycle?
From what I understand, I think it should be A plus 1. So that's where it should start the counter.
So what happened is actually this. So when A is 4, A plus 1 is 5, it will only move the A plus 1 into A at the next clock, the next coming of the clock. At this clock, at this time, when I'm checking whether A is smaller than 5, the A is still holding value 4. So A will only become 5 at the next clock. Correct?
Yeah.
Imagine, okay, remember this. The counter always output the count, correct? The count always output. We always output the count in the counter. So this value we output is the one on the left hand side. So we will see 4 here at the output. And then this value 5 will not be seen at the output when A is 4. Follow me? Can you follow me?
Yeah. Follow. Yes, sir.
All right. So I'm seeing that. So when now we move into the next clock. Now the next clock come in. So A plus 1 get moved over to A. So it becomes 5 now. A is 5 now. So now the operation of this addition will be 5 plus 1 here, and then A is 5. The value of A on the left hand side is 5. The value on the right hand side is 5 plus 1. So when I check A, I'm checking A at this side. Correct?
Yeah.
So I'm checking it. It is 5. So my E will set to 1. So far, so good?
Great.
Follow me?
Follow.
All right. Okay. So now we check for 12. All right. So we continue. We check for 12 is 5. Is smaller than 12. So we go back. We will send the signal back. So we will go. When the clock come in, you still have to count up because it haven't reached 12 yet. So we go back. And then we do the count. All right. We do the count. So it become 6. So 6 plus 1 and 6. And then we check 6. We go back again, 7, 8, 9, 10 until 12. When we reach short 12, the value A is 12. So this side is 12 plus 1. This side is 12. So when we check, okay, it reaches 12. We want to stop. We want to stop. So we send a signal F to 1 to stop. But we only stop at the next clock cycle.
Yeah.
We only stop at the next clock cycle. Now the counter, when we move from here to the next stage to say finish, because we connect the counter directly to the output, this actually will trigger. That's why the counter will become 13, because the finish happened at the next stage. The finish happened at the next stage. That's why we will see it C13 shown at the next stage. Because this operation actually already carried out, it just wait for the next clock cycle. This is a problem in hardware design.
Okay.
Okay, let me demonstrate this in the source code. So I have written the Verilog here. So this is the counter. Let's say counter 12. It have input S, a clock reset. Now clock reset is normally not shown in any graphical design tools because they are assumed. We assume that it will have a clock signal and a reset input. A is a counter output, E is the output. Remember the E signal output, and the F the finish signal output. So we have that. All right, this is the module. Now this is the way to split my design into multiple file. If you are splitting your design into multiple file and you do not want to type a very long iverilog compile command, you use the include pre-processing directive. This is a pre-processing directive. It will tell the compiler, look for this file and look for this file. All right. So I include two separate module file. One is called data path. One is called control. Here is another good programming practice. Make sure your module name and your file name is the same. One way, depending if you are using more modern programming editor or integrated design environment or integrated development environment, you may be able to see the file name here. If you are using more older editor, you will not be able to see the file name. So it's a good practice to include your file name in the command so that you know that this is the file name. You have control. So there's another good practice. Make sure your file name and your module name is the same so that you are not confused. This is for your own purposes. If you store it in different name, there will be confusion. You may easily confuse, especially if your system is very complicated. You may have hundreds of files, hundreds of modules. If your file name and your module name is different, then you may confuse yourself because you will have more name to remember. So it's a good practice to store them with the same name. If you split them like that, right? Why I'm doing it this way? Because this is common. a microprocessor have many complicated parts, and typically there are up to 500 designers to design one CPU chip. So you have to split the work into 500 different designers. They each have their own .v file. So this is quite common in industry. So you may. So I'm trying to mimic the industry practice here. All right. So this is a top design, the counter. Not typically the top design is just you instantiate the sub module, and then you show how the sub module are interconnected with each other. So what happened here is I have the input signal, the output signal, the count, output, the output signal E and F, and then this is the state variable that is not output, it's not shown in the output, you only see inside. So the control logic is a state machine design, and then the data path is a register operation. So you can see matching there already. I'm telling you how matching they are. So when I'm looking at the data path, I ask the questions. What is happening at this state? What is happening at state 1? What is happening at state 2? What is happening at state 3? And what is happening at state 4? All right. I have actually gone when I write this, I have drawn ASM chart. It is shown in the lecture slide. It's not shown. It's supposed to shown. Let me open up. Let's get this. We go to. I think this one is showing. The student one is showing. All right. So this one I have tidied up the. I have tidied up the SM chart. This one have this. So in the Lucid chart, what I have done is I'm showing you the step I have gone through to design. This one I have gone through multiple stage of improving the chart and tidy it up. So this shown that because this, as you can see here, this is a decision box. And this state box immediately following a decision box, I can make a design. This is a design decision. I can make the design decision that I do not need an extra state. I can do this because it's following an immediate decision box. I can reduce the number of states by changing this into a conditional box. All right, this is one thing that you can look at, and this is a simple design decision. I can reduce the number of states. They can hopefully by doing that, I can make my counter count faster. All right. So this is one decision that I've changed. There's a difference. From what is shown in the slide that you can download this from the ULearn. So this become a conditional box because I made a design decision that this should be a conditional box so that I can reduce the number of states. So if I throw this away, I will have only 1, 2, 3 states. So I have T0, T1, and T2, 3 states and three ASM block. And then by checking whether A have reaches 5, I can look at A3. I can look at A3. I know A3 will be 1 because 5 is 1, 0, 1, 0, 1 is 5. So at bit 3 is 1 of A, bit 3 of A is 1. Then I would have reached 4, and I choose 4 because I have run simulation. When it reaches 4, the count output shown 5. So let me demo it to you. So let's go through this. first let me check it can recognize iVerilog. I have checked it. It's supposed to recognize iVerilog here. Okay, it recognizes iVerilog. So I can compile. The name is counter, and then the test counter. So I do not type control and data path here is because I include the file inside. I have included them, so I don't need to specify their name in the compiler line. So it compile. So let's simulate it. Feed it the output file a.out. So it simulated and give me the output. It shown me that when does E change to 1? When A is 4, E change to 1. When A is 4, E change to 1, but actually, this is okay. You know why? You know why it's okay? Even though A is 4, E change to 1, but in the counter at the actual output, it will show 5 at the timing. I know this by looking at the GTK wave. Need to type that GTK wave. The dump file is dump.vcd. Oops, don't want that. Dump.vcd. So I can show you the waveform. Let's expand this. So let's look at E. Look at A4. If A is 4, E is 0. You see when A is 5, E is 1. So there's a simulation output. It works perfectly. So I know that from here, okay? Because, all right. So that's why I can just check one bit, A3. If A3 is 1, I can set E. So let's look at my data path. I'm checking A3. If A3 is 1, I set my output to 1. Now there's another coding tip here. I can show you another coding tip. Typically now when I'm actually designing for teaching purposes, I show it out explicitly. I'm testing A3 whether the value of A3 is 1. I don't need to do that. I can just say if A3. This will work as well. This will work as well because A3 is 1 bit. If it is 1, the if statement will return true, so I can set E. So both will work. So if I do that, I might want to say if A3 is 1, E is set to 1. Make it clear. So I can save. All right. So this is what happened. All right. So let's look at the data path. Once I'm discussing that, let's look at what happened in the data path. Data path, I have input the start signal, the clock, the state, A, E, and F. I know this by looking at the ASM chart. I can still use this. So look at it. So how do I know that? Okay. Now knowing that I have made a design decision to change this into a conditional box, because I can do that is follow a decision box. So this can be a conditional box so that I can group this together with this state to reduce the number of state. to reduce the number of state. The fewer state, then I take fewer clock cycle to count. So when I remove, if this is the conditional state, so if S is 1, I'm going to initialize A, E, and F. So I know that I have to take an input S, and I know that A, E, and F are output because they are on the left-hand side of the state box. Anything on the left-hand side of the state box is an output. So this tells me immediately that A, E, and F are output, S is an input. And then I know that there are no other input aside from state and clock. Because I need to know what state I'm in. So in this case, I'm in this state, so I need to know that I'm inside this state, so I need to fit in the state variable to tell me that I'm in this state. So I need to put in the state variable input. So notice that the state is an input. It's not declared as a reg, it's an input. So in the data path, the state variable is an input to the data path. This also tells you that the data path is controlled by the control logic, which is a finite state machine. The control logic is a finite state machine. The data path is all the operations that happen, and it is controlled by the finite state machine, the digital system. So here I'm using the case statement. The case statement is like the switch case statement in C, but case is much more, what's the word I'm looking for? Much more neat. It's much neater than the C switch case implementation. So case, I'm checking the value of state. If it is 0, 0, I use T0 because I don't like to write 2-bit binary 0, 0 too many times. Even though doing this, I still have to write a lot of time. But it makes it clear that I'm in state 0. Much more clearer, I'm in state T0. So I'm checking S. If S is 1, then I initialize the value. I initialize A, E, and F. I'm supposed to initialize A, E, and F, so I miss out E here. So this is the register transfer operation. So it actually translates directly from the state diagram. So in the state diagram, if S is 1, I initialize A, E, and F. So I can add in here. All right, any questions? So far, so good? Am I going too slow?
No, just nice. I can follow you.
All right. Do you want me to speed up? Or this is just nice?
Just nice.
Okay.
I just had one question. Remember the T1 begin you are assigning the A to A, and then if A just now initially you put a bit 1B1, if I'm not mistaken, previously on that code.
Bit 1, B1?
Yeah.
Oh, okay. You're talking about checking this. If A3. You mean this one?
Previously you had that. Yes.
You mean this one?
Yes. Yeah, this one sometimes I get confused. Sometimes I notice they're very long. They have one B1, some D1. What is the meaning of D1 and B1?
Okay, P is binary. P mean binary. P mean decimal.
Oh.
P is decimal. This is binary. And then you have H hexadecimal.
Okay.
Right?
So that means that this is one means I'm assigning binary 1.
1 bit, this is 1 bit binary. And then I can only show 1 bit value here.
Oh, okay. So even if I do this also is okay. So I can just directly assign it to 1 for this case.
You can directly assign it to 1, yes. But this, as a hardware engineers in the designing, I don't like to do that. I want to be specific, be as specific as possible. This one is for other hardware designers so that they understand. All right, this is a 1 bit value. I'm checking a 1 bit value. This is one. This is just making it explicit. If you just say 1, you don't know whether this is a 1-bit value or not. If I type it like that, then it's very specific. This is a 1-bit value. I'm checking for a 1. Okay?
Yeah, understand.
All right. All right. So I finished with T0. It is a direct translation from the ASM chart. So you look at it. So I'm looking at the block. This block specified by this state. Now this have become part of this is because I make a design decision that I do not need a separate state. If I have a separate state, then the data part will be very different. I have to have an extra state. So I change this to a conditional box. So I can do that here. I can delete this. Okay, I delete that and insert a conditional box there. And then, okay. So if I change it to a conditional box, now this become part of this state. So all these things happen at the same time in this state. I call this state T0. I can insert the text box. There, I call it T0. I can string it. With that. So T0. So T0, and this is part of it. So next state, this is the thing that is happening. All right. So I further tidy this up in the lecture slide to show you how I test for A when A reaches 5. I just check 1 bit A3. I will know that it reaches 5. Then I can output the signal E is 1. And so on. Now I add something else. This is a design error. If I do this, the moment A3 change back to 0, the E will not be 1 anymore. So if I just want to set E to 1, if the count reaches 5, then I shouldn't reset it back to 0. Okay. So what happened here is so if reaches 5, I set E, and then I check A4. Now I check A4. Now this, if A4 is you look at the transitions here, the count. So A3, I should probably type it somewhere here to show. Think of it as a 4-bit value. Probably using this is a better idea. Let's explain this in T1. So in A3, so A is a count of 4-bit value. So at 0, 1, 0, 0, it will count to 0, 1, 0, 1, and then it will count to 0, 1, 1, 0, which is 6, and then 7, and then notice what happened, it changed to 8. The value of A3, can you see is the word too dark? Was you able to see what I typed?
Yeah, can see.
Okay, I can. So you notice A3 will change from 1 to 0.
Yeah.
So this is what I am taking advantage of. So this is 8. So at 8, A3 changed from 1 to 0, and then it will continue counting. 9, 10. You notice is 11. Now we change back to 1, 12 at 12. Notice that? So if you look at the SM chart, when A3 is 0, when A3 is 0, it will not check whether A is bigger than 12. It will not check that. So I can reduce some operation. So that is why I'm checking A3. I don't have to do the operation so many times. All right. Now, here's the questions. Why don't I see A checking for 12 in my data path? Why I only check A3? There are no checking whether A is reaches 12 or not here. Now the reason is simple. There are no such operation here. It's because if you look at the SM chart, are there any register operation after checking A reaches 12 or not?
No.
There are no register operation. I have no conditional box here. So there are no data transfer operation here. So what is this then? Where should I put this? So what happened when A reaches 12? The question you ask is what happened when A reaches 12? When A reaches 12, I go to the next state. And that is telling me that this is a state transition. This tells me that what happened next. That is timing information. So this is not part of the data path. It is not part of the data path. That's why you don't see this here. All right?
Okay.
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 So here I have described all the data operations in T1, and then next state is T2, which is you have only one operation, finish signal, finish. So in the next state, there's only one operation, finish. That's it. So I set the finish signal to 1, and that's it, and done. So I have done the data path, all the register transfer operation is being specified. Now let's look at the state transition. So in the state transition is in the control part, control signals. So in the control here, as you can see, I'm only specifying what are the state, what is the next state, what is the next state, what is the next state. So here, the state is the output of the control signal. It output the state. Output the state. If it's a registers, I output it. Same thing. I use a parameter to because I don't want to write 2-bit binary 00, so I use T0 instead of 2-bit binary 00 to make it clearer in the code. So instead T0, I check S. If S is 1, I go to T1. My state go to T1. So you look at the SM chart. If S is 1, I go to the next state. If S is 1, I go to the next state. If S is 0, if S is 0, I go back to state T0. You look at the SM chart. If S is 0, I go back to state T0. S is 0, I go back to state T0. Clear?
Clear.
Now look at what happened in state 2, T2. In state, T0, next one is T1. In T1, I check A. All right, this is A3 and A4. I'm checking A3 and A4. That's why they are only 2-bit value. So I should right. A is A3 and A4. Remember, there are 2-bit value. 4-bit value, I'm checking these 2-bit 110 whether they are 11. Right? Checking for that. Okay, 4 to 1. 110, 4 to 1. All right. A here is counter. Make it clear. All right. So A here is 2-bit, A3, A4 and A3, checking for whether it have reached 12. When this is 11, that means I have reached 12 because I'm checking for 1100. So I go to state T2. So you look at the SM chart. If it reaches 12, I go to the next state. If it doesn't reaches 12, I go back. So you see, I mentioned that we don't see this in the data path. The reason being is this is actually used for state transition. It's not used for data operation. That's why you see this in the control logic. So this happened in the control logic. In T1, I'm checking A4 and A3, A3 and A4. If they are 11, I go to the next state T2, else I go back to state T1. In T2, automatic go to state D0. T0 is my next state. Default. Now, it's a good idea to always include default, especially in your finite state machine. This is so that when you power up, when the reset signal is not fired properly, you always start in a default state, right? So it is a good practice to have a default state. Notice that in my data path, I do not have a default in my case statement. In my data path here, I don't have a default. I only have 3 value for my 2-bit state variable. My state variable is 2-bit. 2-bit, I'm supposed to have 4 value, but here I only specify 3 value, but I didn't specify the 4th value, and there are no default state. This is okay. Why? Why is this okay? The reason being is in the data path, the data path doesn't control whether I go to which state. This is not controlled by the data path. It is an input. The state value is an input. So if the input is always 0, 0, 0, 1, and 1, 0, it's always these 3 values. So I do not need to care about 1, 1. The reason I do not need to care about 1, 1 because I take care of it in the control signal. In the control signal, I make sure that the state value will always be 0, 0, 0, 1, and 1, 0. It will never be 1, 1. If you go to 1, 1, I say, okay, go to 0, 0. If it is 1, 1, I go to 0, 0. So it is controlled by the controller. So the controller makes sure that the state value is always 0, 0, 0, 1, and 1, 0. So my data path will never see 1, 1. So I do not need to care about what happened 1, 1 because state is an input. Another way to check whether you need to include whether you have the default statement or not, is to check whether the variable you test is an input. Here I know that it is an input, so I do not need to care about not specified value. In here, I need to make sure that we have no non-specified value because it is an output. State is an output. This is an output. State is an output. Because in an output, I need to make sure that all the value are specified. All right. So that's all for the walkthrough. Any questions? We're coming to an end of the lecture. Hello?
No. So the assignment will be on.
Okay. Let me show you the assignment. Here's the assignment. It's on the lecture slide. Now, assignment is to ask you to design a shift multiplier. a 4-bit shift multiplier. I'm showing you what happened. In this case, if I 11 times 3, I'm expecting 33. So this is 11 in binary. 1011 is 11. 0011 is 3. I supposed to get 33, and this is 33 because it's 32 plus 1, 33. But this is a very small multiplier because it only have one adder and one shift register. Right? This is for 4-bit. It's not very small. It is very if the number of bit is larger, it's increasingly getting smaller. The bigger is the number of bits, then the smaller in size relatively is the shift multiplier. So what this does is it do multiplication by shifting, add, shift, add, shift, add, shift. That's what it does. So I will walk you through with the operation. These are the specifications. What if you look at what happened in the multiplication, you are actually you create the partial product and then you add the partial product together. In binary, it's even more straightforward. You just shift the bit and then you add. You shift and add. When you shift, you are doing the multiplication to get the partial product, and then you add, and then you sum up the partial product, then you can form the final product. So we can partition this into using just one adder and a shift registers. So how does it achieve that? So I'm going to show you what happened here. So these are the block diagram showing the register that you may need in your binary shift multiplier. Okay. So we are designing a 4-bit, so I'm going to demo you how are the operations being done in 4-bit. First, you need a counter. The counter will say, okay, this is a 4-bit multiplier. They will tell me that I need to shift 4 times. 4-bit means shift 4 times. 4-bit means the input are 4-bit, so the output have to be 8-bit. The output have to be 8-bit. So I have my input, the multiplier and the multiplicand will have to be fed into register B and register Q. The register Q will hold the input value of multiplicand. Register B will hold the input of multiplier. So I will feed in the 2 value input here. Let me show you what happens if I feed in the input. So this is the initial state. So let's say I want to multiply 9 times 10. This is 9. 1001 is 9. 1010 is 10. So 9 times 10, I'm expecting 90. 90 as output. So I'll feed in the multiplier. This is a multiplier. This is a multiplicand. Multiplicand multiplied by a multiplier. So multiplicand multiplied by a multiplier. So multiplicand I put in here. Put in Q 1001. Multiplier I put in B here 1010. So what is happening here is I will have to calculate the partial product. Every time I shift, I'm creating the multiplication. Every time I add, I'm adding the partial product. So the multiplication will create the partial product. All right. So I need to know when I should add and when I should not be adding. So to do that, I need to check the smallest bit of the multiplicand. If it is a 1, I have to add. If it is 0, I do not add, I just shift. So in this case, what happened here is I check this, it is a 1, I have to add. But before this, I need to update the counter. The counter say I have to shift 4 times. I have to shift 4 times, all right? Because I have 4-bit, 1001. I have to look at all these 4 values, 1001. That's why I need to shift 4 times. to look at all this 1, 0, 0, 1. The first time I look at is 1. So I have 4 times to shift. So let what is happening, what I decided to do is I can choose to look at this first and then decrement the counter, or I can choose to decrement the counter, then look at this and then shift. After shift, then I decrement the counter again. So I decided to decrement the counter again, so I -1 the counter. So the counter become 3. Then I check, look at 1. It is a 1, so I need to add. So 1, 0, 1, 0, add 0, 0, 0. I will give, you will give me 1, 0, 1, 0. So 1, 0, 1, 0, add 0, 0, give me 1, 0, 1, 0, and I store it in A. This hold the partial product. Now this holding is holding the partial product. So I got my first partial product. I have check 1, I have add and then store it in the partial product. Now I need to shift. So I will shift 1 bit. I shift 1 bit in. Now this is a carry. When I have 2 additions, I expect there's a carry output. So this is to store the carry output. But when I shift, I will shift in a 0. This is non-existent. The operation will automatically shift in a 0. If I do logical shift, it will shift in a 0. So I will do a logical shift operation here. So I shift 1 bit. So this 0 will shift in here. This 1 will shift out. I have checked this one. Notice this is the input. This is the input value of the multiplicand. So I look at it, I don't need it anymore, so I discard it. So I shift it out. And then the partial product value will shift into the Q. Right? I shift all this thing 1 bit to the right by 1 time. So it will become 0, 1, 0, 1, 0, 1, 0, 0. Okay? 0, 1, 0, 1, 0, 1, 0, 0. I shift this out. This will be discarded because I look at it already. I don't need it anymore. Now I will check this. But before I check this, I have shift 1 time. So I have shift 1 time. So I need to reduce the counter. I have already shift 1 time. So I decrement the counter first. It become 2. That means I have 2 more time to shift. I have 2 more time to shift. I have 2 more value to look at. I have 0 and 1 to look at. Now I'm looking at this. I have 0 and 1 to look at. 2 more value to look at. Because this is 0, I do not do addition. I just shift. If it is a 0, no addition. So I've checked this value. It is 0, no addition here. So I just shift. So I shift. Again, I have shift. I need to decrement the counter now. The counter is still 2, but I only have 1 value to look at. So I need to decrement the counter. So I decrement the counter. I only have 1 more value to look at. This is a 1 more value to look at. And then again, now I look at 0. Look at this value. It is 0 again. There are no addition. I do not need to do anything. I just shift. So I will shift. All right. So I shift. Now I'm looking at the last value. I do not need to shift anymore. I do not need to shift anymore. This is the last value I look at. All right. So I have no more value to look at next. No more value to look at next. So I decrement it to 0 because the next value is not the input. It is the partial product. Right? This value is the partial product. So now I add. This is a 1. I know that I have to add. So I'll add 1, 0, 1, 0 to 0, 0, 1, 1, 0, 0, 1. It will give me 1, 0, 1, 1. Right? 0 means I have no more next value to look at, but I still need to throw away this value because this is not the partial product. This is still the part of the input. So I need to throw this away. So I shift to throw this away. Once I shift, I have my final value, and this is the value. If you add everything together, it will give me 90. I know that this is 90 because this is 10. This is 5 times 16. 5 times 16 is what? 80. 80 plus 10 is 90. All right? Any questions? Hello?
No, I have no question.
Is it clear?
For me, yep.
Okay. So what you may need to do is you can go and read the lecture slide. Now in the design example, I show you how this can be split into a state diagram. If you look at the state transition, how you move from one state to the other, and look at the state diagram, you can see that they perfectly match. And then how you can look at the state register transfer notation, stating the register transfer operation, and you can translate that from here to there. I have not upload my source code for this. I will upload it after this. I will upload this to UlearnX so that you can play with it yourself. I will include the control, the data path file, the counter, and the test bench, so that you can play with it yourself. All right. So you can contrast them, and then after you've gone through this, then give a crack. Try your hands on how to draw an ASN chart with the given specification here and the operation here. Look at this to understand the operation, how it works, how the shifting works, how the counter works, and when does it supposed to add and when it is not adding. And then by that knowledge, try your hand at drawing the SM chart. All right, draw an SM chart first before you write your Verilog code. So I will create a assignment activity for you to submit your assignment. I'm expecting two things. One is the SM chart. So you can use the lucid chart. You can save it to your desktop, and you can also export it as a PDF file, and then you can submit this PDF file. All right. That's another nifty feature of the lucid chart. So I will expect the probably three, depending on how you write your code, at least two .v file. One will be your design file, one will be the test bench, and then one PDF file, which is your SM chart. Is that clear?
Yep.
Yep.
Clear.
All right. So if you have any questions, you can ask me on WhatsApp or on the Teams chat. You have no more question. I think that's all for today. I will upload the. Do you want to look? I will upload the source code for the counter on after this on UlearnX. Check out UlearnX. Okay.
All right.
If nothing else, we can end this session here. I forgot to record. Someone record?
Yeah, I'm recording it.
All right. Thank you, man. I forgot about it.
All right. No problem.
Okay. All right. That's all for today. Thank you.
Thank you, Doctor.
Okay.
Bye.
Thank you,
All right. Bye-bye.